Bismillahirrahmanirrahim. Assalamualaikum and a very good day to all students. I am Dr. Jeffrey Abdul Razak from the Faculty of Manufacturing Engineering FKP. So for this week, we will move forward to the next lecture for BMFG 1213 subject Engineering Material about the chapter 11 on characteristic, processing, and application of composite. For this offline lecture, there will be 3 pre-recorded video presentation, namely as part 1, part 2, and part 3. So this is the part 1 of the composite lecture. I hope you will enjoy and focus with the learning content and understand whatever point that I'm going to deliver. So up to this level, I really hope you already heard or maybe got a very basic ideas about the terminology of composite. As a common guide to all of you, here are some important outline for this chapter. In this chapter, we are going to learn about the classification of composite material. All right. The characteristics of composite material, the processing of some selected class of commercial composite in industry, which is for this subject, we just focus to the processing of fiber reinforced composite. And last but not least, the application of composite material. For the course learning outcome, just to recap on the course learning outcome, because this is important for you to have a basic idea why I study this topic. So for this chapter, it falls under the course learning outcome CLO number 3. Describe the processing method for engineering material, and for the level of complexity, all right? Okay, so it falls under the application level here. And then we expect students able to apply the knowledge that you learn and using a critical problem solving to describe and maybe to solve the problem related to composite material. So for the learning question, student, the following are some of the questions that at least you can answer after attending my offline class. First, you need to know the main classes and the type of composite material. So for composite material, we can classify them either based on their dispersed phase or based on their matrix phase. Second, the reason why we need to use the composite material instead of other primary engineering material that you already learned previously, like metals and metal alloys, ceramics or polymers. Okay. And then third, how do we estimate or maybe predict the mechanical properties of composite through simple calculation? So the calculation from this topic is not so difficult. Simple calculation, we use the rule of mixture. And then the fourth one, on describing various possible processing or manufacturing technique related with composite fabrication. And last but not least, some of the typical application of composite material in industry. So for the learning outcome, all right, for the learning objective, my apology. So student, at the end of the learning of this chapter, we expect you guys able to define the composite material, to define them in a very technical accuracy. All right, describing the role of constituent in composite, we basically having two major important phases. First is the matrix phase, and the second one is the dispersed phase, or we can call them as reinforcement phase. Please make sure you know each of the function for respective phases. And then the second LO here, to distinguish three different type of fiber reinforced composite, we will learn later. All right. And then third is on the classification of composite material based on the matrix type, the MMC, CMC, and PMC. All right. And then the fourth one on the utilization of the rule of mixture, all right, here to estimate the composite properties through calculation. And last but not least, on various processing methods to manufacture the composite material based product. Here we go, all right? Again, before we proceed further, let us understand fully the terminology or how we can define the composite material. From the slide here, composite can be simply defined as combination of two or more multi-phase material that exhibit a significant proportion of the properties of both phases such that better combination of properties is realized. So meaning to say, the aim of composite fabrication or production is to produce another new material having better properties in comparison with their original material. So in terms of mathematics, it can be simply imagined as when you have A material, you add with B material, and then at the end turn up as C material. Okay, so make sure the A and B material is chemically dissimilar material. All right, so the C material, okay, will come out with better or improved properties in comparison with A or B. But C material are still, obviously, we can differentiate the phases, and then it maintain the presence of A and B constituent. We can make it them different, distinguish them differently or clearly. All right. So in terms of phases, by referring to this figure, one material, say for example, the A material becoming as a dominant material here, will be served as metric phases, okay? And then normally, the metric phases is continuous, okay? And then add with another B material will serve as a dispersed phase here, okay? Where it is discontinuous and surrounded by matrix when we combine them as a composite material. So this is A material, this is B material, this is C material, which is composite material. So the matrix in this case will give the overall shape to the composite bodies and hold the dispersed phase accordingly, right? Meaning to say the composite become as a house, and then the dispersed phase become as the occupants, all right? And then the dispersed phase here play their role to reinforce or strengthen the overall resultant new composite material, all right, or C material. Looking at to your surrounding, normally the composite material are artificially made. So we can say it is man-made. So can you please name a few products at your surrounding made up by composite material? So maybe you encounter them or use them in your daily routine. Your house made from the concrete wall. The concrete is composite material made from the combination of sand, gravel, cement, and metal wire mesh. Another example, maybe you can look at to your family car. The automotive tire is composite made from natural rubber as continuous phase, the matrix, and added with many ingredients such as the carbon black particles, all right, as dispersed phase. What else? You can name it maybe one or two example by yourself, and then ask yourself, whether it is composite material or not. Okay, so this is how the composite material look like. So this is the characteristic of matrix and also the dispersed phase. Remember, matrix must be continuous or dominant, and dispersed phase must be discontinuous, and it's surrounded by the matrix material. So student, please also bear in mind that there are also naturally occurring composite material in your nature or at your surrounding. For example, wood consists of strong and flexible cellulose fibers, right, which is surrounded by the stiffer lignin. The cellulose fibers, the dispersed phase, and the lignin as a matrix phase. Your bone in your body, all right, which built from soft protein collagen fibers and hard hydroxyapatite mineral as a matrix. So look at here, so beautiful the architecture of composite at the surrounding as the natural composite available in the nature. Okay, so next, after we understood that the composite are made up from the matrix and dispersed phase, most composite have been created basically in mind to improve the combination of mechanical characteristics such as stiffness, toughness, and strength at ambient and high temperature. Hopefully you can recall back all these terms that you already learned at chapter 6, the mechanical properties. So by looking at to this figure, all right, these all figures, we should know that the properties of composite are a function of the properties of the constituent phases, the type. So we need to understand what are the matrix used and what are the dispersed phase used to build the composite body. All right. And how about the relative amount? So some of composite we put at the little amount of dispersed phase, and some of the composite we put at the higher amount of dispersed phase. So absolutely, their properties are totally influenced by the concentration used. And about the geometrical shape of the dispersed phase we use here, some of the reinforcement or dispersed phase having the rectangular shape, some having the circles, some having the cylindrical shape. So these are all influence the surface area on how the matrix can interact with the dispersed phase. All right. So the geometry of the dispersed phase in this context means the particle shape, the particle size, this is the particle shape, the C1, and then the distribution and orientation, this is how the distribution and orientation look like. Some arrange continuously side by side to each other, and some alternating look like this, all right? And then these are all the factors that we need to consider when evaluating the properties of composite, okay? So let's move forward to the next slide on the role of phases. Even though I've just mentioned about the role of matrix and dispersed phase just now, so let's review again, okay? The continuous phase, or easily referred as metric phase, can be a polymers, metals, or ceramics. Always bear in mind these all three important engineering material. So in composite, the metric phase play the role to bind the dispersed phase together. This is the function of the metric, to bind the dispersed phase together. So it also protect the phases from environment, and most important, it distribute the load or transfer the stress to the dispersed phase during the loading. Because now the matrix we can imagine becoming as the body of the composite. And then it also shield the composite, the overall body, from the damage due to the handling. So the metric at the end will give the bulk shape of the composite. So this is the role of the matrix. First, they house or protect the dispersed phase. This is your matrix. So the composite material can be classified in terms of their matrix phases. It can be metal matrix composite, the MMC, and then it can be also the ceramic matrix composite, the CMC, and PMC for polymer-based composite, polymer matrix composite. Next, we will discuss on the role of discontinuous phase, or known as dispersed phase. The main purpose of dispersed phase addition in composite is, of course, to enhance the matrix properties. Normally, the matrix properties are weak. That's why, in order to improve the weakness or limitation of the matrix properties, then the reinforcement phase or dispersed phase come. So the role of dispersed phase are basically different based on the matrix used. All right. So as you can see here, if we add the dispersed phase in MMC, it actually perform the function to increase the yield strength, the tensile strength, and also the creep resistance, which is the strength of the composite or the characteristic of the strength at an elevated temperature, at higher temperature. While for CMC, the ceramic matrix composite, due to the brittleness characteristic of ceramic material, the presence of dispersed phase basically could enhance the toughness or the K1C value for the produced CMC. You see here, the toughness behavior. What is toughness? The ability of material to absorb the energy. Because of the brittle nature of ceramic, it easily experience breakage or broke due to the loading. So by having the dispersed phase can stop the propagation of the crack, so that the composite material, the ceramic matrix composite or CMC, having the higher ability to sustain with the increased toughness. So for the polymer matrix composite here, the PMC here, we understand that the polymer is lower performance in terms of temperature or high heat environment. Okay, so by having the PMC here, we can enhance the modulus E, the yield strength, the tensile strength, and also the creep resistance, as well as the performance at higher temperature. All in all, the dispersed phase may be classified in terms of the particles, fibers, and structural here. Okay, all right, hope up to this level, you can differentiate what are the function of the matrix and what are the function of the dispersed phase and what are the matrix and the dispersed phase is all about. So let's move to the next slide on the classification and characteristic of composite. The classification and characteristic of composite can be based on the dispersed phase itself. All right. So there are three divisions of classification, namely as particle reinforced, okay, fiber reinforced, and structural type composite. And at least another two subdivisions exist for each of them, for each of the major classification. So, for example, particle reinforced, we know as the equal X in terms of their dimension, meaning to say at all direction, it possesses similar length or similar dimension. Means that the dimension are approximately or same in all direction. The particles are classified either as larger particles, okay, and dispersion strengthened for smaller or finer size particles. But for fiber reinforced composite, the other category here, this is the first category, and then the second category of classification based on the dispersed phase. All right, the dispersed phase has the geometry of large length to diameter ratio. If the particle reinforced, we can see like a spherical or particulate in their shape. But for the fiber, they having certain length, all right, the larger length here with smaller diameter ratio. We call them as L over D ratio, all right. It can be continuous aligned fiber for long fiber or discontinuous for short fiber, which has two orientation, either as aligned discontinuous fiber or randomly oriented discontinuous fiber. Meaning to say, in one matrix body, even though the fiber is discontinuous, but the arrangement is aligned, or the other sub-classification, it may be random orientation. So, for the next third classification of composite material based on their dispersed phase characteristic is the structural composite, whereby the structural composite is a combination of composite and homogeneous material in the form of laminates or sandwich panel. So the discussion in this slide and next following slide will be organized according to the classification scheme as in previous slide. Okay, so we will start first with the particle reinforced composite. As we understand here that the particles are equiax, having similar dimension at all direction, okay, and the particle should be small in its size and distributed uniformly in the matrix phase for better composite strengthening mechanism. All right. So there are two sub-classification for particle reinforced fiber, as you can see here, all right, which are large particle and dispersion strengthened for finer particles. Okay, the classification basically in terms of their size. One sub-classification for the larger size particle, and then the other classification for finer or smaller size particle. And then the difference between both of them are actually based on their strengthening mechanism. So for the larger particles and the smaller particle, they absolutely give different effects in terms of the strengthening mechanism. The term large here basically indicate that the particle matrix interaction cannot be treated on the atomic or molecular level. So in general, we can say that the larger particle having the particle size larger than 10 micrometer. All right. And then the particle matrix interaction cannot be treated on the atomic or molecular level. So for most of the large particle-based composite, the particulate particles basically harder and stiffer than the matrix. So that's why it can reinforce the composite by restraining the movement of the matrix phase and hold the fraction of load where the matrix transfer the sum of the applied stress to the particle during the loading. All right. So the degree of reinforcement or improvement of the mechanical properties are actually depends on the strong bonding at the matrix particle interface. All right. So the best example of the large particle reinforced composite are the concrete system, okay, which containing the cement as the matrix and the gravel with sand as the large particle. So also another example can be viewed at the following slide here. All right. So as you can see here, in this slide, we expose with three common example of large particle composite system. As you recall back with the understanding of metal alloy, we have the spheroid steel. This is the example of metal-based composite. Okay, so we have the matrix here, the alpha ferrite matrix, okay, behaving as a ductile matrix. Okay, so after we do some sort of heat treatment, okay, we can produce the intermetallic cementite particle, the Fe3C, okay, which behaving brittle and is found well distributed within the ferrite matrix. So the presence of the cementite here basically increase the strength of the spheroid steel. And then the second example here, as you can see, the ceramic metal composite, or we call them in short as CEMAT. CEMAT. The most common cement is the cemented carbide. Cemented carbide is WC, the tungsten carbide, all right, reinforce the cobalt matrix. Okay, so for this example, it basically composed of extremely hard particles of refractory carbide ceramic. For example, the tungsten carbide here, which embedded in the ductile cobalt metal matrix. This cement composite is basically we utilize them as a cutting tools or hardened steel, for hardened steel, okay, because of their superior hardness performance. All right. As you can see here, the large volume percent of the tungsten carbide particle is utilized. Okay, about 100 minus 10 to 15. Okay, say for example, we take 10. Okay, about 90% is the reinforcement phase. Thus, it will give maximum abrasive action could be obtained from this ceramic composite. The next common example is the automotive tire, which is made from the natural rubber. So it reinforced with the various particulate material. So as you can see your car tires at home, okay, they basically use the rubber, but we understand the rubber material is basically softy and very tacky, all right, very soft material. So without using the reinforcing particulate material, the natural rubber based tire are not able to perform their function. So the carbon black we add here as a final particle obtained from the hydrocarbon combustion, okay, basically responsible to increase the toughness, okay, the stiffness and also abrasion resistance of rubber, for better rolling performance of the tire, especially on the road. Okay, and as you can see here from the microscope image, there are dispersion of carbon black particle within the rubber matrix, which having strong adhesive bonding with the natural rubber matrix. Okay, natural rubber as a matrix. So the next example of the large particle reinforced composite is on the concrete system. So basically, the concrete having both matrix and dispersed phase. The dispersed phase and matrix are both ceramic material, but due to different characteristic of ceramic A and ceramic B, it can also be classified as composite. Okay, those ceramic for concrete material like gravel, the sand and cement are required to produce the concrete. And but why sand and gravel? Because of the finer size of the sand and then the coarser size of the gravel. So the sand can pack into gravel void. Okay, okay, this is gravel and then comes sand here. So there is stacking effects. Okay. All right. Another reinforcement technique involved in composite concrete not only by the particulate reinforcement, but they are through the reinforced method concrete, the reinforced concrete method. We can have here the reinforced concrete, the pre-stressed concrete, and also the post-tensioning strategy. For reinforced concrete, normally we use the Portland cement, the Portland type cement concrete, okay, for structural and building application. So this Portland cement concrete can be further reinforced when we adding the reinforcement like the road, the remesh, the wire, the bars or rebar, okay, which we let it embedded into the fresh concrete and uncured concrete. Okay, thus the reinforcement basically, okay, how they increase the strength, they render the hardened structure capable of supporting greater tensile, compression, and shear stresses. So when the concrete experience the crack, okay, the reinforcement available at the inside the concrete, okay, can give them still maintain to sustain the load. Right. So another reinforcement technique for strengthening the concrete involve the introduction of residual compressive stress. Okay. So we can discuss based on pre-stress and post-tensioning. Okay. We understand that the brittle nature of the ceramic material are stronger in compression loading in comparison with tension. If we apply the tension, the ceramic material, say for example, in this context, the concretes are easily experience the breakage. So in pre-stressed concrete, the high strength steel wire, we position them inside the empty mold and stretch with high tensile force. So after the concrete has been placed and allowed to harden, okay, we basically release the tension, okay, and then as the wire contract, okay, they will put the structure at the end under compression, okay, because the stress basically now are transmitted to the concrete via the concrete wire bond. Okay, so the next step of concrete strengthening is post-tensioning here. Okay, so we can see the difference here for the post-tensioning method. The stress here basically we apply, okay, after the concrete becoming hardened. The compressive stress will be imposed on the concrete piece when the night we tighten them, okay, to the wire, to put the wire under tension. When we give the compression by tightening the nut, okay, the wire inside here is in the tension mode. Okay, so normally all this pre-stressed concrete is usually prefabricated and commonly we use for the highway and railway bridge application. Okay, so next, this slide, okay, we'll discuss about another sub-classification of particle reinforced composite, which is the dispersion strengthening. Okay, for the dispersion strengthening, the particle size are finer. Okay, the difference between the large particle and the particle, for the strengthened particle, we use the smaller particle and even finer at between 10 to 100 nanometer, 10 to 100 nanometer. So this finer particle is very hard, and inert material, either metallic material or non-metallic material. Normally for non-metallic material, we use the oxide type. Here the Thoria is one of the oxide type. For dispersion strengthening, the particle matrix interaction has lead them into the atomic or molecular level reinforcement. Uh, in comparison to the larger particle, the interaction not go down into the molecular level, but for the dispersion strengthen, the strengthening mechanism is down to atomic or molecular level due to their finer size. So the strengthening of the dispersion composite involve interaction between particles and dislocation within the matrix, where the matrix hold the major load while the particle basically hinder or impede the dislocation motion. Both of these situations may at the end restrict the plastic deformation, which improve the yield, the tensile strength, and also the hardness of the produced composite. We have two examples here for the dispersion strengthened composite. All right. The properties of high temperature strength of nickel, nickel as the body or matrix here, was significantly enhanced when we add the thoria. Thoria, we just add about 3%. Thoria perform its function as reinforcement material. And then the thoria is basically finely dispersed in nickel matrix. So the next example here, we have the sintered aluminum powder, or in short, we call them as SAP, whereby a very thin and strong adhere alumina coating is formed on the surface of extremely small aluminium flakes. All right, yeah. So one of the important factor that basically influence the properties of particle reinforced composite is the concentration or the volume fraction of particles, other than smaller size of particle and evenly distributed within the matrix for effective reinforcement. Okay, yeah? So now we will talk a bit about the mathematics. So volume fraction of both factors may influence. Okay, we have the metric phase, we have the reinforcement phase, or the dispersed phase. All right. So the volume fraction of both factors basically may influence the resultant behavior of composite. Okay. As a rule of thumb, we can say that the mechanical properties will enhance with the increasing of particle content. So if we have the volume fraction of particles increase, the mechanical properties also will be increased. So for this slide, it shows that there are two mathematical equations that have been formulated for the relationship between the elastic modulus of composite with the elastic modulus for each constituent, the matrix and particulate, with the volume for matrix or volume fraction for the particulate. And then these are called as a rule of mixture because we have the mixture between the dispersed phase and the matrix phase. And then this equation basically can predict the elastic modulus that can be fall between the upper bound properties, meaning to say higher performance properties. So this is the first equation of rule of mixture. All right. So the elastic modulus here, the E composite, is basically equals with the E composite, basically equals with the E matrix, multiplies with the volume fraction of matrix, the VM, plus with the E particulate, the elastic modulus of particulate, multiply with the volume fraction of particulate material. Okay, all right. So this equation we call them as the upper bound equation. While for the lower bound equation is referring to this second equation. All right, the second equation. All right. The elastic modulus of resultant composite EC is basically equals with the multiplication product of E matrix with the E particulate. Okay, the modulus of matrix that we use multiply with the modulus data of the particle that we use, divide with the modulus of matrix. Okay, multiply with the volume fraction of the particulate, plus the modulus of particulate multiply with the volume of matrix. Okay, this is the formula at the denominator. All right. So next. So now we have the graph to show you about the upper bound and lower bound. Let's have a look to this figure plot on upper and lower bound elastic modulus. When EC, the composite versus the volume fraction of particulate. Okay, so this is the EC, the modulus of composite with the volume fraction of the particulate. All right, for this case, we add the tungsten here with the copper. The tungsten as our dispersed phase and the copper as our metric phase. Okay, the experimental data point are actually fall between the two curves. When we do the baseline fit here, we can see there are two distinguished different plot characteristics. We have the upper limits. This is the upper limit, the upper bound, and then we have the lower limits of composite. We call them as a lower bound based exactly on the rule of mixture. Actually, both of the upper bound and lower bound equation are not only can be used to calculate for the elastic modulus. So it also can be applied to other properties. Okay, we just, for example, if you want to determine the electrical conductivity here, just replace the modulus here in the equation with the conductivity, electrical conductivity, the sigma E. And then same goes to the thermal conductivity K here. If you want to calculate here, okay, so for the upper bound, say for example, we have the E composite equals with E M V M plus E P V P. So if you want to calculate for thermal conductivity for the composite, K plus C for the particle, the electrical, the thermal conductivity of the particle times with the volume fraction of the particle. So this is how you manipulate the equation of the lower bound and upper bound to determine or to predict the properties of the composite based on the volume fraction that we add in the composite for each constituent. So next we go to the slide about the classification of the fiber reinforced composite. We actually finished discussing the particle reinforced type composite. Okay. The second type of the composite classification are based on the geometrical shape of dispersed phase, which is the fiber reinforced composite. Student, what make the fiber are different with the particles? Of course, their geometrical dimension. If the particle having the equiax dimension, similar length at all direction, okay, but for the fiber, it will have different certain length to diameter ratio characteristic. Okay, so due to the length factors and fiber orientation, for fiber reinforced composite, it can be classified either as continuous aligned fibers or discontinuous short fibers. For these later category, it can further classified either as discontinuous short aligned fiber, okay, or randomly oriented discontinuous short fibers. All right. So for the short fibers, the fiber length are too short, whereby it produces a significant improvement. It still produces the significant improvement in strength. Okay, so for fiber reinforced composite, they are technologically important where most of the design goal that using fiber in composite are to obtain high strength, but at the very lightweight characteristic because the fibers is very strong. Okay, so it provides significant strength improvement to material. It has either rod or tubular-like structure. Okay, like rod or tubular structure having circular or flat cross section, having the circular, like cylindrical or rectangular cross section, tubular structure. All right. So the length to diameter, okay, value, we define it as aspect ratio. Aspect ratio. This is the aspect ratio. All right. Normally, the typical L over D for the fibers are ranging from 30 to 150. All right. Okay, unitless because length may be in millimeter, divide by millimeter for diameter, so unitless. So example of fibers are like glass fibers, carbon fibers, and many more. So continuous glass fiber in polymer matrix composite, where the strength are due to fibers and polymer matrix are simply hold them in place. Okay, so if in PMC we have polymer as matrix and then reinforced with the fibers, the polymer matrix will hold the fiber in place. All right. So just to refresh your understanding on the function of the fibers. So next, we will discuss further about the aspect ratio on fibers. We will again detailed explanation related to the aspect ratio in this slide. Okay, just to recap that the aspect ratio defined as the fiber length divided by their diameter. Okay, so have a look to this figure comparing between the fiber A here and then the fiber B. Okay, so fiber A having larger diameter but quite short in its length. All right, for long thin fiber referring to fiber B here, they often provide superior properties, but a bit expensive and difficult to manufacture. To produce the thin fiber is really difficult, as well as quite challenging for us to disperse it in a uniform condition while in the composite bodies. So while for small aspect ratio fibers referring to fiber A, lower L but larger D, okay, that's why having smaller aspect ratio, okay. Typically, it will provide better compressive stress properties, but composite with short fibers in it are typically less resistant to damage propagation in comparison with the fibers having a larger L over D. All right. So in this comparison figure, it shows that the orientation of long fibers, which is continuously aligned, you see here, the long fibers that are continuously aligned, while the short fibers here are randomly oriented. You see here again in the table, okay, not again, but this is the first time table being showcased, the relationship between length and diameter of cross-sectional D, all right, or aspect ratio. The lower the D value, the higher the L value, all right, yield the bigger aspect ratio, the mathematic here, all right. L over D, the lower the D, the higher the L, the higher the aspect ratio. As you can see here, for the nylon case, longer DL length and lower diameter. All right. So next, for the fiber reinforced with regard to the aspect ratio, basically we can further classify them just by referring to the L over D value. The fiber material is further classified on the basis of their diameter and the characters. So we will have the viscous type, viscous macam makanan kucing, viscous, the fibers itself and the wires. Okay. Whiskers in Malay language, we call them as sesungut. Okay, so let's see the difference between them. For whiskers, it possess extremely large aspect ratio. Okay, because they have L over D, larger value of L, and then finer value, thinner value of D. And then virtually, these whiskers are free from defects. Normally, it produced from the thin single crystal. Okay, we produce thin single crystal. That's why we can control them so that free from defect and not polycrystal. Example of whiskers are like graphite material or carbon whiskers, silicon nitride, silicon carbide, and alumina whiskers, Al2O3. Since it is too small, okay, in terms of their size, high crystal perfection can be expected. So it was extremely strong due to their finer size. But we are not using it extensively. Please remember, because to having whiskers in industry, it's really, really expensive in terms of its cost. Okay, so next category for the fiber is the fibers itself. If viscose is made from the thin single crystal, the fibers are made from the polycrystalline, either polycrystalline or amorphous, yeah, that having small diameter also. So generally, the raw material for fibers making are ceramics and polymer. We have polymer fibers and ceramic fibers. Example of fibers are like alumina fibers, aramide. Okay, this is the polymer-based fibers. We call also as Kevlar. All right. E and S glass. Okay, we have two kind of fiberglass. E referring to the electrical type and S referring to the strength type, okay, mechanical type. The carbon fibers, the silicon carbide fibers, boron and UHMWPE fibers, ultra high molecular weight polyethylene fibers. So the last category of fibers is wires. The difference between the wires with the fibers and whiskers is on their relatively large diameter. Example of wires are like steel wires, molybdenum wires, and tungsten wires. Typical application using wires are like wire mesh for pre-stressed concrete or radial steel wire reinforcement in automotive tire. So for the concrete, we have the wire mesh here, and then we place at the building site, and then we pour with the concrete, let them harden together. All right. So this wire mesh will act as the reinforcement to the concrete body. Same goes to the radial tire. We put the layer of wire here so that it can perform as the reinforcement. So for the next slide, okay, it showcases you the fiber reinforced composite. Okay, we should understand that their fiber orientation or alignment. The fiber concentration and its distribution are all factors that give the significant influence to the general strength or other properties of fiber reinforced composite. Okay, now in terms of fiber orientation, there are basically only two extreme possible direction of loading, force loading. A parallel alignment here, okay, parallel alignment we call as longitudinal axis of the fibers in a single direction, or the totally random alignment. Okay, this is totally random. We can see here the continuous fiber are normally aligned, whereas the continuous fiber here are normally aligned. Okay, this is discontinuous. This is continuous fiber because the length are quite long. Okay, in comparison with the discontinuous one. But the discontinuous fiber, it can be aligned or randomly oriented or partially oriented. Okay, so as a rule of thumb, better overall composite properties are yielded when the fiber distribution is uniform. Yeah? So before we made any analysis on the effects of fiber reinforcement to the mechanical behavior of composite, okay, we must know beforehand the relative properties of both constituent phases between the matrix and fibers. At least we need to know what are the strength of the fibers that we use, what are the strength of the matrix that we use, and then what are the volume fraction between the fibers and the matrix. Only then we can predict the properties by using or performing the calculation. So the following slide, okay, this slide is just showing you the pattern configuration of fibers in fiber reinforced composite. we can have the discontinuous fibers in fiber reinforced composite, okay, and randomly oriented, okay. This is discontinuous and randomly oriented. Discontinuous and aligned pattern, okay, like this. And then for short fibers, continuous and aligned pattern for the long fibers here. And interestingly, we also have the fabric pattern here like mat, okay, like tika mengkuang here. Also, we can have in our composite as one kind of fiber orientation. We also do have this kind of fabric pattern where the fiber arranged in the specific weaving pattern. Kita anyam dia. Just to highlight at this slide that for continuous and aligned fibers, the fibers is longer than the critical length where it enough for load being optimally transferred, okay, from here during the loading. So we will further discuss about the critical length later after this. For this continuous aligned, okay, the fibers are basically shorter. These continuous, the fibers are shorter than the critical length. So we can expect here that the discontinuous fiber basically provide less effective strengthening mechanism for composite that we produce. But using this fiber is a little bit cheaper and maybe faster and easier during the fabrication process, especially for manufacture the complicated composite shape. And then for the random type of fiber, we also call them as a discrete or chopped fibers here. Random and discontinuous fiber, we call them as a discrete or chopped fiber. The strength is not high as with aligned fibers composite system like this, okay? But they can give us isotropic condition, meaning to say isotropic, the properties are independent of direction. If we talk about aligned fiber, the strength are in anisotropic condition. Isotropic, bukan isotonic drink, okay, but isotropic where independent, the properties is independent of direction, but for the continuous is anisotropic. Okay, right, next. Just to recap on the role of matrix as continuous fiber in fiber reinforced composite. Okay, the matrix can be metals, can be polymers, or can be ceramic. So utilization of polymers and metal is when the ductility or flexibility is desirable. So while in the case of ceramic, we are more interesting to improve. We are more interested basically to improve their fracture toughness in composite making. All right. So the role of matrix in fiber composite, reinforced composite is basically like particle reinforced composite. Basically first to bind or hold, okay, to bind or hold the fibers as reinforcement or mechanically supporting the fibers in its place. Due to the continuous faces, the matrix give shape, okay, to the fibers, give shape, all right. And then to share or to transfer the load, okay, to share or to transfer the load, all right, to reinforcement, to the dispersed space for composite strengthening. So it also prevent, okay, the propagation of brittle crack. In addition, matrix also will protect the environment, the reinforcement from the surface breakage, from the surface damage. All right. So build up the bulk form of composite and then prevent the propagation of brittle crack. Okay. So next on this slide, okay, I am just to share the microscope image of the fiber reinforced composite having the aligned continuous fiber as their dispersed space. At the left side here, okay, here is the cross-sectional view for metal matrix composite of alpha molybdenum matrix, okay, alpha molybdenum here, all right. Which is ductile and being reinforced with gamma nickel aluminide. Okay, gamma nickel aluminide here becoming as a dispersed phase, right? And then gamma aluminide here is brittle in its nature. As you can see here, at this cross-sectional view, we cut them into cross-sectional surface. The nickel aluminide fiber was properly arranged. They arrange very homogeneously arranged within the matrix of alpha molybdenum matrix, giving optimum strength at the fiber direction. So at the right side here, okay, another example giving you the fracture surface of ceramic matrix composite consists of glass as continuous fiber matrix reinforced with silicon carbide fiber. So glass here becoming as a matrix, the continuous phase, and silicon carbide becoming as a dispersed phase as the fibers. Okay, so this MC was fabricated by the glass slurry method. So glass slurry method, where we melt the glass and then we pour into the silicon carbide fibers. All right, so the fracture surface morphology image, as we can see here, the silicon carbide fibers are well interacted with the glass matrix. Okay, so I think this is the last slide for part one. Just now in previous slide, we are exposed with aligned continuous fiber reinforced composite, but in this following slide, we are having the discontinuous random two-dimensional fiber reinforced composite as example. So we take it, for example, the carbon reinforced carbon, the carbon as a matrix reinforcing the carbon material in carbon reinforced carbon composite. Okay, sound very unique, right? So the carbon fibers which are very stiff, okay, and strong reinforce the continuous carbon matrix which are very less stiff and very less strong. So the process to produce this kind of composite is by dispersing the carbon fibers or pitch. Okay, dispersing the carbon fiber or pitch, and then we burn it out at extremely higher temperature up to 2500 degrees Celsius. And then you can see here the randomization of the carbon fibers, all right, has let the fiber lie in two-dimensional plane. All right. So this kind of composite that we use, okay, for application like a disc brake, considering of good lubrication of carbon material as gas turbine exhaust flaps due to high temperature of carbon material itself. So we also can use as a nose cones for the aerospace application. So other than this two-dimensional randomization here, okay, two-dimensional randomization, okay, the carbon fibers also can be arranged in other variation of three-dimensional and discontinuous one-dimensional random orientation. So I think this is the end of part one, and please stay tuned with me for the following part two and part three offline lecture of this chapter. So with that, I thank you. Assalamualaikum warahmatullahi taala wabarakatuh.